you very much for introduction. Today I'm going to present a very precise mobile device tracking mechanism that allows your mobile devices used as a mouse in the air. So this is a joint work with Yi Chao Chen and Professor Lily Chiu and UT Austin. So these days, many people are using the smart devices and people are surrounded by smart devices such as smartphones, smart TV, laptop, tablet, and smart glasses. So for some of the smart devices, they require very complicated controller to fully utilize their functionality, but unfortunately the provided controller is not good enough. For example, with smart TV, you can do almost all things you do with the tablet and laptop, such as web surfing and social networking and gaming, but the provided controller is not good enough to utilize these applications. Also, for the smart glasses, it usually has some small touchpad that can recognize some simple gestures such as swiping and tapping, but the number of distinct gestures is too few, so it significantly limits the usability of smart glasses. So ideally, we believe the remote controller for smart devices is using our hand movement. If our hand movement can be very precisely tracked, then it can be transformed into the mouse cursor movements, so we can control the device just like we use mouse, even without requiring the flat surface. So in this work, the goal is using your existing mobile devices to recognize your hand movement very precisely, so it can be used to control the other smart devices such as smart TV and laptop and glasses and some small devices in Internet of Things. So here the main challenge is how we can precisely track the movement of the mobile devices. So regarding the tracking of the mobile devices, there have been many existing works. So the most popular works are using the RF signals such as Wi-Fi. So Wi-Fi-based device tracking and localization has been very popular these days, but these are not sufficient for the mouse capability because it only supports the sub-meter level accuracy. So accelerometer equipped in the mobile device is also supposed to track the movement of the device, but the error of the measurement is really huge, so the accuracy is not sufficient. Using the gyroscope, you can track the rotational movement of the device, and it is indeed used for some of the commercial air mouse devices and the remote controller for smart TV. But actually, it tracks the rotational movement and transforms the rotational movement into the two-dimensional movement to change the position of the mouse. But sometimes it's intuitive to users, so users do not know how much exactly the mouse button will change by their wrist movements. So sometimes it means users having some difficulty in controlling the mouse cursor. So in this work, we introduce audio-based mobile device tracking mechanism that especially uses the Doppler shift generated while the device is moving. So here, the smart devices emit the audio signals using their own speakers in inaudible frequencies, and the mobile devices that needs to be tracked records the audio signal and transform back the signal to the processor, and the processor tracks the movement of the mobile device by analyzing the Doppler shift of the mobile device. So regarding the device tracking, so some people might wonder, why not simply use the accelerometer? Accelerometer is equipped in almost all mobile devices. It's really cheap to access in terms of energy efficiency, and conceptually it's supposed to give the position information by double integrating the measured acceleration. So it has two fundamental problems. First of all, acceleration is really sensitive and easily affected by the gravity. So very small vibration that is not avoidable while the user is holding the device, it already causes non-negligible acceleration. So in this figure, we show some measurement result of the acceleration while the device is moving and the tracking using the accelerometer. So according to the ground truth here, the device started its movement at 1 second and stopped its movement at 4 seconds. But if you see the measured acceleration, the difference while the device is moving and not moving is not significant. So it's really difficult to tell when the device started and stopped. So it means that the measured output, the quality is pretty low. The signal to noise ratio is really low. Moreover, the acceleration-based tracking is really, really sensitive to noise. So very small acceleration error is accumulated over time and quickly grows up. So here, if you see the tracking result of the accelerometer-based tracking, so the error grows over time, and even if the device has stopped at 4 seconds, it keeps going to total wrong direction, and because of the accumulated error in 3 seconds, it goes to wrong direction, infinitely goes to wrong direction. So Doppler shift is basically the shift of the frequency that is incurred by the movement of sender or receiver. So it is incurred, basically the functional relationship between the velocity and the Doppler shift is shown here. So if you assume the sender is not moving, then by observing the Doppler shift, we can estimate the velocity of the receiver. And it turned out that it's much more accurate than the accelerometer-based tracking. So if you see the Doppler measurement result here, first of all, you can very clearly tell that when the device starts movement and stops its movement. It means the noise in the measured Doppler is very small. Also, the movement tracking result here is much more accurate than the accelerometer-based tracking. So in the remaining part of the talk, I will explain how to track the movement using the measured Doppler shift. So for the accurate tracking, the most important thing is accurately estimating Doppler shift. But simply estimating the Doppler shift does not immediately give you the position information, because it only gives the distance change from two speakers. So from these distance changes, we have to find the exact location of the device. Also for the localization, we also need to know the distance between two speakers, and we have to address the issue of the uncertainty of the initial positions. So I'll first explain how to accurately estimate the Doppler shift. So to estimate the Doppler shift, we first need to observe the signal in the frequency domain. So for that purpose, to observe the change of the spectrum in time domain, we perform the short-term Fourier transforms, SDMTF. So by doing this, we can see the change of the spectral magnitude of the spectrum in each sampling interval. So here, left figure is the spectrogram of the audio signal. So we find the amount of the frequency shift by finding the frequency with the maximum magnitude. So by subtracting the center frequency of the original signal, we can find the amount of the frequency shift incurred by the Doppler shift. So here, the right figure is the Doppler shift to be estimated by the peak detection. So if you see the Doppler shift estimation result here, you see some spikes, which is likely to be error. So this error makes tracking inaccurate, so we have to find some way to improve the accuracy. So to improve the accuracy, first of all, we use the larger spectrum. So unlike the RF spectrum, the one which is very precious, audio spectrum is not used by humans, so we can utilize the larger spectrum to estimate the Doppler shifts. So instead of sending the signal in one specific frequency, by sending them in multiple frequencies with sufficient interval, we can increase the measure, we can receive the more samples for the Doppler shift estimation. So here, so that left figure is showing that the 5 different measurements for the same movement while the device is going up and down. So to combine these results, we can perform the maximum ratio combining, which is widely used for the receive antenna diversity. But before performing the maximum ratio combining, we try to further reduce the error. So our observation about this, the Doppler shift measurement is sometimes it has unnecessarily high spikes, which is likely to be error. especially if you consider the limit of the human movement speed. So human hand movement speed is kind of limited, but if it is the Doppler shift is too high, it's likely comes from the error rather than the real human hand movement. So specifically, if the Doppler shift change from the previous shift is larger than 10 Hz, we regard them error and we remove this thing as an outlier and combine the other things. So if you see the combined result, the result is much more smooth than the individual Doppler shift estimation. So the next thing is how to locate the device based on this accurate Doppler shift estimation. So for the localization, we first need to know the information about the distance between two speakers. We have to handle the issue about the uncertainty of the initial position. So I first assume that these two informations are known, and later I will address these two issues. So basically, when the Doppler shift is estimated and we already get the information on the previous position of the device, then finding the distance from two speakers is quite straightforward. It is, we can update the distance from previous distance by measuring the change of the distance during one Doppler sampling interval. So the velocity is calculated from the observed Doppler shift, and by multiplying it with the Doppler sampling interval, we can find the new distance from two speakers. Then once we find the distance from two speakers, actually finding the position is finding the intersection between two circles. So here, I will illustrate how to continuously track the device position from the initial position. Here, for the tracking purpose, we construct a virtual coordinate where the left speaker position is 0,0 and right speaker position is d,0. So here, given the information of the initial location, from the Doppler sampling Doppler shift measurement result, we can find the distance from two speakers. Then once we know the two distance, we can find this position x1, y1 by finding the intersection of two circles where the center points of the circles are the location of the speakers, and radius is a distance from two speakers. And we continuously repeat this until the tracking has finished. Then the next question is how to find the distance between two speakers. So one easy way to find the distance is asking the user to measure it using the rulers. But it's annoying to users, and sometimes users do not know exactly where the speaker is located inside of the device. So here we provide a very simple but effective way for the calibration that can easily find the distance in a few seconds. So in this calibration, we request the user to move the mobile device from left to right side, and while user is performing the scanning, the speakers are generating the audio signals and the Doppler shift is measured. Then using the measured Doppler shift, we can easily find the position, the timing when the device is at the left speaker and at the right speaker. So when the device is at the right speaker, the Doppler shift changes from the positive to negative, so we can easily detect this timing. Also, when the device passes the right speaker, again the Doppler shift changes from the positive to negative. So once we know this timing, we can again find the distance the device traveled by iterating the velocity measured from the Doppler shift. So the last question about the tracking is how to handle the uncertainty of the initial position. So here, let me briefly talk about this. So because we do not know where the device will start its tracking, so for the area that the device will potentially start its tracking, we allocate the particles. So here, we utilize the particle filter approach. So each particle corresponds to the initial position of the device. And whenever the device is moving, we change the movement, change the position of all of the particles. And whenever we perform it for some of the particles that gives impulse of movement, we filter them out. And using the remaining particles, we find the movement of the device by averaging all of the movement of the remaining particles. So by repeating them during the tracking, we can keep reducing the number of remaining particles, and it's converted to possible area of the initial position. So now I show some performance evaluation result. So for to validate the feasibility of the real-time processing and for the purpose of the user study, we implemented the real system of the tracking and it performed the user study. So for this experiment, we used the frequency range between 17 to 19 kilohertz, and the Doppler sampling interval was 40 milliseconds. So for the performance comparison, we also implemented the acceleration-based tracking, and we also attached the camera on the ceiling, and we collected the ground truth of the movement of the mobile device using the camera-based tracking. And we also implemented the gyroscope-based tracking that translates the rotation movement to the two-dimensional movement. This is because this is widely used for the commercial air mouse devices. So during the user studies, in this user study, 8 users were involved, and they all registered beauty, and we evaluated the tracking accuracy, and it's mainly compared with the accelerometer, and for the usability is mainly compared with the gyroscope. And we had 2 different kinds of evaluation. One is the pointing the target. We show some specific target on the screen and ask the user to point it. And for the drawing, we ask the user to draw some simple shape like a heart and circles and something like this. So for the tracking accuracy, we show from the corrected result, the trajectory error that is calculated by comparing it with the ground truth movement was the median was around 1.4 centimeter, and even 90% error was about 3.4 centimeter. And one important result is it wasn't affected by the background noise. We generated background noise by playing some music using the same speaker we used to emit the inaudible signal, so which is a realistic scenario. So it wasn't affected. It didn't affect the accuracy. It's because the frequency of the music was pretty different from the frequency of the inaudible signal. And for accelerometer, the error was almost tenfold higher. So for the usability evaluation, we compared here we evaluated the ability the user can point a specific target. So here the metric is the ratio between the actual travel distance to the shortest distance to the target. So ideally it should be close to 1. So if you see the result from our scheme and the camera-based tracking, the median is close to 1, and even some worst cases, the differences of our scheme is not very significant. But on the other hand, when the people use the gyroscope, they sometimes have some troubles when trying to to point a specific target, because they do not know exactly how much they have to rotate their wrist to move their pointer. Especially if it's in diagonal direction, they have some troubles. So likewise, we asked the user to draw some simple shape, and it shows the similar difference. So when they use the gyroscope, they have some troubles drawing the original shape. So so I want to talk about some limitation of our scheme. So one of the fundamental limitation of our tracking is the accumulation of the tracking error. This is mainly because we track the position by the velocity tracking. So velocity, rather than finding the absolute position, we track the position by finding the velocity. So velocity error accumulates over time. So we basically think this is not very sensitive to users, because users are more sensitive to instantaneous error rather than absolute position error, slowly accumulated over time. But we are trying to resolve these issues. Also, the issue we recently found while we prepared the demo is affected by multipass. So in the crowded environment, the accuracy reduces. So the possible solution will be using some additional data from the audio. So for example, if you see the time difference of arrival for the signals from left speaker and right speaker, by using them along with the Doppler shift, we can find some kind of absolute positioning rather than the tracking. So yeah, we believe it will helpful to reduce the tracking error accumulation. So in this talk, I introduced the audio-based device tracking, and we show that we can realize the air mouse using this technique. So first of all, it achieves the centimeter level accuracy. Also, one of the important benefits of our scheme is it doesn't require any additional hardware, and it can be all implemented in software level, so you can immediately use this technique without any change in the hardware. So the possible future will be further improving the accuracy and make it more robust, and extending it for the 3D localization to make it have more applications.